All right, welcome. Today we're going to crack open a really powerful algorithm, one designed to find the absolute truth inside some incredibly complex systems. Let's get right into the junction tree algorithm.
You know, when you think about it, so many things in the world are just these tangled webs. Whether it's genetics, the stock market, or even your social network, you've got all these different variables, and they're all nudging and pulling on each other. You tweak one little thing over here, and the whole system can react in ways you'd never expect.
And that's the real puzzle, isn't it? When things don't just flow in a straight line. When A affects B, but B loops back around and affects A. Well, trying to calculate anything becomes a total nightmare. It's like the ultimate chicken and egg problem, but with hundreds of them all influencing each other at once.
But what if I told you there's a brilliant way to solve this? That's what we're looking at today. The junction tree algorithm doesn't try to wrestle with that messy web head-on. No, it does something way smarter. It completely restructures the problem, turning that tangled mess into a clean, simple tree where the right answers just fall out. Okay, so to really get this, let's put on our detective hats. Imagine you're standing in front of one of those classic investigation boards. You got all your clues pinned up, those are your variables, and you've connected them with string to show how they're all related. That board, that's our model of the problem.
And you can see the two kinds of cases right here. On the left, you've got the easy one. It's just a simple chain of evidence. A leads to B, B leads to C. Piece of cake. But look at the right side. That's the hard case. Our investigation board is a total mess of loops and feedback. Clue A affects D, but D also loops all the way back to influence A. This is where finding the exact truth gets almost impossible.
And when I say almost impossible, I mean, well, just look at this number. If our detective board had just 100 clues and each one could be true or false, trying to check every single possibility by brute force would mean looking at over 2 to the 99th combinations. That number is so astronomically huge, it's basically never going to happen big. You just can't compute it.
So, if brute force is out, what's the clever path forward? Well, this is where the genius of the algorithm really shines through. The big idea is, don't solve the messy web. Untangle it first.
And this is the real aha moment. Our detective realizes that just staring at that tangled board isn't going to cut it. The real solution is to take all the pins off the board and reorganize everything into a new structure that actually makes sense, one that doesn't have any of those confusing feedback loops. So to start that reorganization, we need a new kind of building block. And that building block is called a clique. It's a simple idea. A clique is just a group of clues on our board that are all directly connected to each other. So, the suspect, the weapon, and the location might all be tied together with string. Bam, that's one clique. A little cluster of related evidence.
Now that we have these little evidence clusters, what do we do with them? Well, we build something totally new, called a junction tree. And the core idea here is that each node in our new diagram isn't a single clue anymore. Instead, each node is one of those entire clusters, one of our cliques. We're building a tree made out of clusters, and that's how we get rid of those messy loops.
But hold on, you can't just throw these clusters together and call it a day. For the whole thing to work, for the math to actually give us the right answer, this new tree has to follow one very, very important rule. It has to be consistent. And that rule is called the junction tree property. It sounds a little technical, but the idea is actually pretty intuitive. All it says is that if a single clue, let's say it's a muddy boot print, shows up in a few different clusters, then all of those clusters have to form one single unbroken path in our new tree. It's what keeps the story of that muddy boot print consistent across the whole investigation.
And you can see exactly why this matters right here. Look at the tree on the left. It's broken. The clusters that share a clue are disconnected, which means the information can't flow correctly. It creates contradictions. But the one on the right, the proper junction tree, it's perfect. All the clusters with that same clue are connected, guaranteeing that evidence is shared consistently across the entire system.
Okay, so we know what we want to build and why it's so important. Now, for the really fun part, how do we actually do it? Let's walk through the recipe for cooking up this perfect tree.
So the whole process really happens in 3 main phases. First, you have to prep the original graph. That means adding a few clever new links to break up the worst loops, and then identifying all those key evidence clusters, or cliques. Then you build the new structure. You lay out all your cliques and figure out the strongest, most important connections between them to form that perfect loop-free junction tree. And finally, you put that new tree to work. You load all your original probability data onto it, and then you let the clusters talk to each other, passing messages back and forth until all their beliefs line up perfectly. Once everyone's on the same page, you can just ask any cluster for the exact probability of any clue you want. And just like that, case closed.
Now, this whole thing sounds amazing, right? Almost too good to be true. Well, that brings us to the big trade-off, because this much power always comes with a price.
So first, let's talk about the power. The single biggest benefit is enormous. This algorithm gives you the exact answer. I mean, not a good guess, not a pretty close approximation. It gives you the stone-cold 100% correct probability every single time.
But you know what they say, there's no free lunch. And that is especially true here. Getting that perfect, exact answer comes at a cost, and it's a computational one.
And that cost has a name. It's called tree width. The easiest way to think about tree width is as a sort of complexity score for your graph. It's basically determined by the size of the single biggest, most complicated evidence cluster that gets formed during the whole process.
And here's the kicker. The time it takes to actually run the algorithm is exponential in that tree width. So if your problem is so tangled up that it creates even one monster-sized clique, then even this incredibly clever approach can grind to a halt. It becomes just too slow to be practical.
Which really leaves us with this final, fascinating question. In a world full of shortcuts and good enough approximations, when is it worth paying a potentially huge computational price to get the absolute, provably correct answer? It's a trade-off that sits right at the heart of AI, machine learning, and really any kind of complex problem solving. It's a huge question and something to really chew on. Thanks for digging into this with me.